Okay, online. So Google Slides seems to work very well. So we'll keep using that. And all right, again, welcome back from spring break. Any of you went to Miami? Spring break, spring break haven. But anyway, it's not bad here. All right. So here's the plan for today. Honey, can you see the slides?
Yeah, yes, Professor.
Okay. Great. Hopefully, you had time to catch up with the neural network materials. I posted two videos that go through basically the same process conceptually and hands-on, the process of training a neural network model we call MLP, multi-layer perceptron. Very similar to the case with lattice regression, but this time it's more complex. As you know, the model structure is more complex, involves more steps. The backdrop is like much more complex, and a little bit more math going on. And then you include the regularization and include a few more extensions, and that's even more complex. So take your time in watching the videos. Watch it twice. Need it, watch it more time. The classic saying though is the more you put in, the more you get, right? And these are not any simple concepts. The point is to that you become familiar with overall process and then the inner steps to the point that you feel comfortable, jumping step, not jumping in terms of when you do the hands-on, you jump and skip steps, not like that, but if you pick and choose a point in the process and you feel, familiar, knowing what's the previous step, what's the next step, knowing the overall structure and down to the details of the steps. What does the step do? What are these elements that are involved in this step, such as when you calculate the forward prop is not very different, but back prop is very different. We're talking about two layers, back propagation. And then, if you're in the output layer, back prop, what are these? You have the weights and bias, two data structures separately, right? And then two layers, meaning two weight matrices, one for each layer, and then two bias vector, one for each layer. So much more stuff. First time around you'll feel lost, but if you review it more times, you'll get familiar. You'll find a way to, feel confident in the middle of the steps. The point is that you can completely do it, and even if something breaks down in the middle, you are able to find clues to debug and fix the problem. So that's the point. And this is important because you'll be tested on the final. The final exam will be in a very similar format as the midterm exam. The kinds of questions that you'll be asked, and then the level of the level of familiarity with the hands-on part that you are being tested. Expectation is very similar, but the topics are different. And of course, it's more complex. To demonstrate a complete loop process for MLP, it takes more time, takes more steps. Anything breaks in the middle, it's harder to debug if you're not familiar. So that's the expectations. Since the videos are there and the videos, is reviewed and you can play back. So I'm not going to demonstrate the process in class because it sounds seems very redundant. So we'll rely on those videos when you need them. So here, I'm mostly going to, first of all, we'll talk about the midterm exam results very briefly, and then today I'm planning to use the time for you to install, if you haven't, install the open source packages for neural networks from Google, and because the plan is to use them in the final project. So sooner or later you'll use it. So why don't we install it as the last session on neural networks, and then we'll do some practice rounds here, answer some questions, do some exploration here, tweak things around and see what happens, and then get you set up. I didn't make any video on how to use Tensorflow and Keras, so today's class will kind of serve that purpose, and it's recorded. So we'll put it online and you can play back. So that's the plan. And so midterm exam, the majority did very well, as you can see, and as you already know the scores. For those in the red zone, we'll talk. We'll find a way to help you, and of course, you know that if you ask for help from classmates, you'll be confident that you'll get some help, right? You're not alone if you need help. I know things are tough, especially if you're working, you don't have the time. Essentially, the one element that's the most critical is time. How much time you play, right? How much time you repeat the process and have time for questions and resolve any challenges. But I feel that there's still a way to help. So don't be shy, and let's work together. So for the majority of class, I don't have to review the questions, right? Because since most of you did very well, you know where you got points taken, even if it didn't work out during the exam. I know that you have a way to work that out offline, right? You have the exam questions. I'm sure it's probably a few mistakes, or I think it's one of the conceptual questions. What's the best way to find data issues? We touched on very briefly in the class in data science session module. I think the warm-up module. Mostly it's the data exploration stage, right? And the specific techniques would be to use summary statistics for those numeric variables. If you look at distribution, that's going to be the summary statistics, means and standard deviation, min and max. You can quickly find outliers or, interesting, bizarre, or strange distributions. And or if it's categorical variable, then you can do visualization. Plot the bars, you can see strange bars, strange labels. So, it's a small, it's an important point, but also it's a small point that's buried in the materials, I guess. And then if you didn't pay attention to that, it's easy to miss that point. But at least after the fact. All right, so midterm is over. If you have any questions, let us know. I can, demonstrate for you. But for most of you, congratulations. Good work. It's hard work. How much time would you say you spend in this class compared to other 6-level classes? Is it more work or less work? I'm not going to take points from you. If you say something wrong, there's nothing wrong. What do you think?
6357.
Okay, so I guess my courses take time. If you compare to other courses that I don't teach, like some DMI's elective courses or the database course, which one has more work? Yeah, I figured, because I mean, you have to understand these subjects and do well when you have to interview with companies that do real data work. You have to go through those 2 rounds, 3 rounds, 4 rounds coding sessions, because I heard from our graduates, it's not work, but it's a lot of reward as well, Anyway, that's good. So for today, I'm mostly going to focus. We still have to turn on. So I'm mostly going to focus on open source packages for today. And just a quick note. Desktop. So I'll demonstrate TensorFlow Keras, mostly using the class demo for neural networks, but the additional material version. If you want to go along, download that, and also in today's session, you'll install TensorFlow and Keras if you haven't. For MLP using NumPy, there are extensions which is new to this class. Is mostly unique to MLP neural networks. They are, I mean, regularization is not unique to MLP, but all the others. We introduced here because there's a need for these extensions to increase the efficiency of training. And then it's also possible to implement these in using Python codes in NumPy. So that's why we introduced these. Specific coverage of each of these mini batch gradient descent, you need to implement a inner loop within that loop to implement mini batch. And the coding is intensive, but the process is, it's rewarding to understand the process because all of the modern open source packages for neural networks, all of them implement that. So it's important to understand those. It's fun to, and also challenging, but it's fun and rewarding to be able to implement that and to understand the process using Python codes. Validation curve, that would be the same concept with the logistic regression. Alternative activation functions to solve some of the limitations with sigmoid activation function, and sometimes can also help you increase the training efficiency. All of these points are covered in detail in another video. I just released that. So if you let me talk about two videos that are new. One of them is in today's folder. I mentioned about lecture 6, part 1 and part 2. These go through the differences between logistic regression and neural network so that you understand a new kind of platform, a new structure. And then number 8, the lecture 8, mostly go to the loop process. Today I released this video. This video talks about several things. And several things, but mostly, I think it's toward the second half. It mostly go through in detail about mini batch and alternative activation functions. These are implementation using Python, the logic, the process, and the code. So make sure you go through them. This week while you're still on neural networks. So that's one video I would like to mention. Another video is about managing data sets. I posted probably 2 weeks ago, but I did mention it. If you go to if you recall, in one of the classes, I talked about conceptually how to manage different data sets in a supervised learning project conceptually. This is the video that I had to make another video because that recording on the class wasn't good, it wasn't clear enough. I made another video basically talking about the same thing, but the join is improved. If you didn't know that I posted this, make sure you watch that. This is only conceptual, but the conceptual process provides a guide for the hands-on process, as you know. So that's the conceptual. And then I made a follow-up video. Go back. I think I put them in here in the model evaluation stage. This is going to be the last module for the supervised learning. And then it's going to be the last module that's going to be useful when you do the project, because the next module is going to be unstructured data analysis, and the project doesn't involve that. So I put it here. This is understanding how to deal with how to pre-process the different data sets from the hands-on perspective. So this video maps with the conceptual video, but this one focuses on how to do it hands-on, right? So when you do the project, you make sure you refer to both videos, the conceptual level and hands-on, and make sure you understand why we're doing this here, understand the process, and also implement the process. You'll need to adjust some of the codes, of course. I'm using the demo data sets here. But hopefully the concept is clear. So for some of these topics, in case of MLP, refer to that first video I talked about. The class recording. Any questions? Were you able to find some time to make some progress on MLP concepts? Today is the last week, and next week we will move forward with model evaluations. So we'll be talking about accuracy and then other metrics to evaluate model performances, such as false positive and false negative. So if you haven't completed, make sure you go through all the materials about neural networks. And you also have homework 3 due next week. Yeah. So that will include, most of them will be neural networks related, and a few questions about evaluation that's going to be talked about next week. All right. If you have any questions about MLP, let me know. So we will go ahead and talk about open source. Why use open source? So popular open source packages for artificial neural networks, TensorFlow and PyTorch. The most popular two packages. They're quite different. I'm not used to PyTorch. I'm more used to TensorFlow. They are on very different framework. So, but if you have passion and if you have ambition, you want to achieve more in data science space, PyTorch might be the next topic that you want to conquer. Right. So that's my advice. It's not easy. It's challenging. It's a different mindset, but it's still Python. Right? So you know the basics already. So at least you have a platform to move in that direction. Scikit-learn also has neural networks, but it has less capability for customizing the models, I guess. Okay, so the next demo is going to be based on this Jupyter notebook. So make sure you go ahead and download. I think it's here somewhere, or maybe in that folder. Should be in this folder here. Demo for more materials. Demo 4 is based on demo 4 is based on NumPy coding. It doesn't use open source packages. So NumPy and pandas, mostly NumPy, to implement all of these extensions. But demo 4 more materials demonstrates how to use Keras, basically, from TensorFlow. So go ahead and download if you want to follow along. Well, I encourage you to follow along because, why not? You'll have to install it sooner or later. Oh, by the way, the teams have been assigned, and you can go to Blackboard. Go to final project teams. You can see your teams. And some of you sent your preferences for teammates. I honor that. But in return, you are going to work very hard. I expect more from you. Anyway, so go ahead and download, and I have opened here already. So let me fix the numbering thing. Okay. Honey, can you let me know if you can read them clearly?
Yes, Professor.
How about this? Can you read?
Yeah.
Okay. Students here, can you read? All right, so these are the packages that you already have. But when you do this, run these, and I made some slight changes. So if you want to know the version that you have, uncomment this line, uncomment that line, run them and see if you have any error. If you have error, then that means you don't have TensorFlow. I think you don't have to install this for now. Only install TensorFlow if you don't have it. Okay, we'll wait for you to be ready. The installation process takes some time, so be patient. My version is not necessarily very new, but it works. Raise your hand if you have already installed TensorFlow. You did already, great. Yeah, so we'll wait for the rest of the class to install. Have you already reviewed these? You did? Okay. You run through all of them? Any questions for me? So you're like the best student. No, the best students will talk more. So try to talk more. That's right. And here, the random state, you don't have to. So when you learn it, sometimes it's good to have something that you can replicate, so that you can you can be sure that you get the same results as I do. So I use random state or random seed. But when you do a project, it's better not to have a random seed, because then if some seed doesn't work, you're stuck and you always get that problem. So when you do the project initially, it's better to comment out these lines or completely remove them after you have almost done the project or near the end of it. You can include, randomly pick a random seed and then use that random seed throughout your solutions to see if that works again. And if that's the case, then you can keep using that seed. That's how that helps to make sure when I download your work and I rerun your work, I will get the same result as you reported. Otherwise, because the randomness is going to change. The result that you report are not going to be the one I get exactly. So, but initially, it's better not to have the seed.
Yeah.
Let me see. It's on or done?
Yeah.
Done? It's on. Done, everybody? Okay. Great. How about you, honey? Have you installed Tensorflow yet?
Yeah.
Okay, great. So, we'll use the same data set as the demo. And here I have this open. So we're going to compare the results across by using two methods. Here in module 4, we use Python. We use NumPy to implement the MLP. And then we'll see if we get similar results or if there's difference, why the difference in TensorFlow. So just simply run these codes, mostly reading the data set and checking. And one more word about managing the data sets. So we have the train and test. ER means train, ES means test. We use the transformers to transform the input variables in training sets. Remember what we do? For interval variables, we normalize the variables, and for neural networks, we would recommend using range normalization min-max. So after pre-processing, those variables will have minimum 0 and maximum 1. For categorical variables, we use 1/2, converting them to dummy variables. So the dummy variables also have 1 and 0, right? So minimum 0, maximum 1. So that's why when you look at the pre-processed variable, the minimum are all going to be 0 and the maximum are 1. Very clean. Very clean. And then we use the trained transformers to pre-process the test set. We don't retrain the transformers, as I said in the videos. So that's not going to guarantee that the test set pre-processed data have the same minimum and max. Mostly the case, but not always. If you look at the test sets, for all of these columns, you have minimum 0 and maximum. For up to 7 columns, you have minimum 0 and maximum 1. Very clean. Starting with these columns, some of the minimum is slightly different from 0. The maximum sometimes are kind of far away from 1. You have 1.6. You have 0.5. Can you think of a reason why some of these are very clean, 0 and 1? Some of the others do not have the same minimum and maximum. Or why are some of these columns having the same range as a training set, but some of the other columns don't have the same 0 and 1 range? Can you think of a reason?
Is it because for the test data we don't use the fit transform, we only use transform?
Yes, that is that's intended, right?
Yeah.
And then because we do it that way, we may not observe for the test sets, we may not observe the range of the pre-processed variables to conform to the training set. But again, why? Some of these do conform as well, but some of the others, most of the others don't have exactly the same 0 minimum and 1 maximum. But why? If you look at the mean between the training set and the test set, that for the same column, the mean remains to be very similar. You know, even with those that are quite different, that have quite different maximum. Column 18, the maximum is almost 60% higher, but the mean and standard deviation are quite similar. So the distributions are similar. My question is, why these columns will have the same minimum and maximum, but the other columns don't have the same? Think about the two kinds of variables.
So the flag variables will have like 0 and 1 exactly, and continuous variables will have deviations in the minimum and maximum.
Yeah, exactly, right? So for categorical variables, it's going to be converted to dummy binary variables. And it's always going to be 0 and 1, right? So the minimum cannot be anything different from 0. The maximum cannot be anything different from 1. There's only 0 and 1. So that's why if you check the original data set for this credit card default, you'll find that there are maybe 3 categorical variables that are converted into 7 binary variables after one hot encoding. So that's why for these 7 columns, the minimum and the maximum remain to be 0 and 1. That makes sense. And you expect to see that for all the other variables, these come from interval variables. You cannot guarantee them to have minimum 0, maximum 1 after being pre-processed, because the conversion is not trained on these data sets. They are trained on the training set. We simply use that minimum and maximum from the training set to recalibrate theory. And then the differences are understandable. They are okay. They won't cause any trouble. And then it's a good check-in mechanism for you to verify that your pre-processing stage is conducted, correctly. If you see all 0 and 1 for minimum, maximum for even for the training set, you know that something was done wrong. It's refitted, and that's not good. The reason why we don't refit those pre-processing transformers, I think I talked about it before, but if you want me to explain more, let me know. And so by the same logic, you will expect your score set to have similar properties with the test set, right? Because you pre-process score set the same way that you did with the testing set. I hope that's clear. In the hands-on demonstration for managing data sets, I make the exact same point by using another data set. All right, and then to make neural network work, we also need a one column data set for the Y data. So that's why we make it and then convert them to NumPy. Because that way you eliminate some of the issues in matrix calculation, and then check in the dimensions again. Okay, so the neural network structure is like this. The input data has 24 dimensions, has 24 columns. And then we create a hidden layer, which has 7 hidden neurons. The output layer, because we have a binary target variable, the output layer has 2 neurons. So it's 24, 7, 2. And so it's here. Very handy. That's the structure of the neural network. We keep the parameters the same. So the Python demonstration go through the loop in detail for once, and then reinitialize, and then run the loops in epochs. So if we use Python codes, this is the volume of codes that we have to process. That involves forward prop and then backward prop. And here, let's do a direct comparison. How many epochs did we do? 1,000. After 1,000 epochs, these are the coefficients that we have. And then if we look at the cost curve, it's mostly very similar to the literature question or analog, but you have these, tremendous backtracking or reversing of the cost value, even higher than the very first epoch, which means the model is not the model, but let's say the cost curve, when it does the weight updates, it kind of went to a region where it's even worse than when it started. So, and this is mostly because we calculated the back prop. We calculate the gradient descent based on the entire data set. Based on the entire data set, when we do optimization, when we do gradient descent, if the values are, slightly larger, if the values of the weights and values of the cost are slightly larger than normal, and then because we have the learning rate, the two extremes, if they multiply, it's going to produce a weight update that is too much, as we demonstrated in the very beginning in the analog model. If the learning rate is not selected well, then the cost function will explode, and the weights will explode. That's what happened here. It didn't explode, but it's reversed somehow. But then it quickly, fixed itself somewhere here around 20 or 30 epochs, and then it happened again somewhere here. So the the overall process is smooth, but there are steps in the process that kind of, that degrade it significantly. So the solution to solve this is to use mini-batch gradient descent, where you chop the entire data set into hundreds of smaller sets, and then do the gradient descent on each of the set and update weights, hundreds of times within each epoch. That's the basic idea of mini-batch gradient descent. The benefits is that when you use a smaller data set, it's not going to, it's not very likely to have exploded weight updates. So it's less likely to produce, jitteries like these. And it's going to produce something that's much more smooth, even though it means training more time sometimes because you have more computations to do. So that's what we hope to find by using the mini-batch gradient descent when we use the Tensorflow. So here, keep the same structure. So defining a model is easy. So we define a model that is similar to here. Then we need to create two layers. This is the data. This is data that's not a, that's not part of the model. It's the input data. So here we use the Keras sequential model object. The first layer is going to be the hidden layer. For the hidden layer, we use dense. For hidden and output, with both of them, we use dense layer. The most fundamental layer of neural networks. We need to define the dimension of that. So how many neurons do we need in each of these layers? The 7 and 2. We use D and T to model. Unique to the first layer is it also needs to specify the dimension of the data. It's mostly how many columns are in the input data. We don't have to specify how many rows because it's automatically taken care of by the model, regardless of how many rows that you have. But the number of columns in the input data you need to specify correctly. And then we need to specify activation. For now, we use Sigmor as the default to compare with Python solution. We give them name. These are free-form name that you can choose yourself. And then the model structure is defined. And then that we can summarize the structure and parameters of the model. The next step in Keras is to compile, which means basically to define the computation side of it. The model definition defines the structure of the model, but it didn't define anything else. The computation side mostly involve the gradient descent and the mechanism of that, any mini batches, and things like that. Oh, and how do you define cost? And then what kind of model evaluation metrics do you need? I added these for the purpose of demonstration. Before that, I only have accuracy because in the other side, we only use accuracy to evaluate the model, but we also use loss. We also use the cost function. And for optimizer, the most basic version is SGD, which means stochastic gradient descent, which means mini batch. So stochastic means using mini batch to manage the exploding cost function. So it involves mini batches. Okay. Now we can run, and at this point, the model hasn't trained yet. And this is the last line that you will run before the model will train. Use the model object to call the fit. It's a good practice to be familiar with the documentations for the tool. And that's what I always do. When I have a question, I go there. When I need to implement something, or when I want to look at the options that I have to implement this model, I'll go there. And you can find a lot of resources here. So TensorFlow sequential, this huge page includes a lot of things or links to things that will be useful. So the first thing I want to find is the method fit. So the page structure, some goes like this, some introduction, some examples, and then arguments. Arguments are those parameters that you use to define sequential. So you need to provide layer, you need to provide name. Attributes are what you can get after the model is trained. Here we will test some of these. We'll test in the end, we'll get the weights, right? So we'll need to use the layers. We'll also need to check the model evaluation metrics. So you can check the metrics name. These are defined. These are the way that you define the model object. Methods. One of these is fit. So if you want to find ways to train the model differently, you can look up different ways. So the basic components here is you have to provide X and Y data. For neural networks, both X and Y have to be two-dimensional. You know, X is the input data that has to have M number of columns, and Y data should have T number of columns. Here it's 2. All right, so we have the X and Y. Mini batch size is the smaller sets, the size of the smaller sets you want the model to divide into. And we define it here. It's typically 16 or 32. And the way it goes is typically 2 to the power of an integer. Don't let the integer what's the report? Okay. Anyway. So it's typically 16 or 32 or 64, 128, or 256. So it's 2 to the power of 4, 5, 6, 7, 8. Don't get too large. You know, don't make something like 2 to the power of 12, 13. That's gonna be too large. But don't make it too small, like 2 to the power of 1 to the power of 2. That's going to take much more time to train. So, you know, a balance would be somewhere along 2 to the power of 5 or 6. So that's mini batch, and epochs is, you know, epochs. How many do we have? Let's test run for 10. Let's test run for 100. And then you don't have to redefine the model. The only thing that's involved that changed is here. So and for both is you dictate how many outputs do you need, how much details do you need. Verbose 1 and 2 are not very different. And verbose 0 means it doesn't print anything. So I would suggest we use verbose number 2. So as you train, it's going to tell you each epoch the training result on the training set. Click that to, to shorten the output. And here, in every epoch, it says 188 out of 188. What is 188? 188 is the number of mini batches that is, as a result of the mini batch stochastic gradient descent. The data set, the training set, has 6,000 rows, and each mini batch is 16 because is 32. 2 to the power of 5 is 32. So if you divide 6,000 by 32, you get 188 or close to 188. So that's how many mini batches or how many gradient descent or gradient calculation it involved in every epoch. So every epoch it calculated gradients for 188 times and update the weights for 188 times every epoch. So that's what mini batch mechanism does. It updates the weights more frequently by using smaller sets to avoid dramatic changes in the weights. So that's the reason. We're done with 100 epochs. And then, I mentioned that the metrics, when the model is trained, you can look at the performances of the model. And then what can you look up? It depends on how you define the model. It's in the compilation set. So here, every model has a loss. We define the loss as the same way that we define loss function in logistic regression. And then we also ask the model to calculate accuracy. So these are the two metrics that the model will keep track of. You can call metrics name that is demonstrated here. The sequential model has attributes. Where's the attributes? Has attributes metrics names. The metrics that the model keep track of. That is stored in the history object. So when you call that, you'll see that we're keeping track of loss and accuracy. And later on, and earlier I had, different specifications here. Later we can try that. And also, you can check out the layers of the model. When you only look at layers, you don't see too much information because there are too much information in there. You have to unpack them. We have 2 layers. So you use indices, index position 0 and 1 to access the different layers. What I want to see is I want to compare the weights. So after training, using NumPy, here it's 1,000 epochs. After 1,000 epochs, I get weights, as large as 2 or 3, something like that. It started with very small, in the neighborhood of 0, and it gradually grow as it learned information from the data set. The weights keep going up. After 1,000 epochs, by using a NumPy solution, I get weights close to 3.5. Let's look at the TensorFlow. So to see the output, this is the output layer. Output layer has 7 upper layer weights has 7 rows and 2 columns. Then, the 2 columns is for the 2 neurons in the upper layer, and the 7 rows corresponds with the number of neurons in the hidden layer. So we have 7 by 2. To access the output layer, it's the index value 1, and then you specify weights. And then you get a TensorFlow data object that's very similar to arrays, but unfortunately you don't have those methods that come with arrays, such as, for arrays, I can do list, maybe. For arrays, I can do shape. I don't have shape method or attribute. So these are different from arrays, although very similar. These are TensorFlow data objects. I don't even know much ways to use these objects, but if you go very deep into TensorFlow, you will learn these. All right, so after after 100 epochs, I have weights as big as 2.1. So, so it's increasing, it's learning, but 100 epochs doesn't get you too far. And if you look at the training set loss, this is average loss. Loss is close to 0.4, accuracy barely 80%. And if you compare that with let's see, if you compare that with the NumPy solution, what's the cost? Well, it didn't calculate average cost, it calculated the total cost. So you can't compare that. But accuracy we can compare. After 100 epochs, we get to close to 80%. How about here? 100 epochs is more than 80%. So in some way, the initial efficiency of NumPy solution is bigger, but you see these, jittering. There's a large boundary of going back and forth. It's not a smooth line. It's a, kind of a jigsaw lines. If you zoom into this region, the reason is because there's no stochastic gradient descent. The weights the weight update is sensitive, very sensitive in this region. So the solutions sometimes improve a lot, but degrade a lot as well. So it's time to let's get these sequence of values instead of look at the final result. So we need to we'll skip that for now. We need to extract both things. We need to extract the cost value sequence, and we also need to extract the accuracy sequence. So those values are packed in history. You use history to get stored values, and then what are in the stored values? Stored values is a dictionary. It's a dictionary, so you can take a look at the contents by calling the keys. So the store values has two things. It has loss and accuracy. Each of these are the arrays. So loss is an array of 100 epochs results. Accuracy is 100 of them. So in this chunk of codes defines a plot with two subplots, and the first subplot will plot the loss values. So similar to here, we'll plot the loss values, and then the second subplot will plot the accuracy value. So let's take a look. All right, so in 100 epochs, this is the trajectory of the training process. Cost function improved, fairly well in the first 2 epochs, 2 or 3, and then it slowed down dramatically, and then kind of follow a linear pattern here. But if you compare that to the NumPy solution, NumPy efficiency is huge. It's very good initially. The cost function is able to drop almost 70% entirely in the first 10 or so epochs. So, but later on it has troubles, as you can see. So the initial benefits of using stochastic gradient descent is not good, but it's only initially because the training is not over. Let's do more training and we'll see. So this time, go all the way back to these parameters. Let's do 500, right? Redefine it. And then this time you'll have to redefine the model. So rerun these codes. Oh, yeah, also let me add something here. Later on, when you study the model evaluations, you will learn additional ways to evaluate models, such as false positive rate, false negative rate, and those are very fun stuff. We'll talk about cancer, and we'll talk about a fire alarm, and how to evaluate models based on the business case. So here is all technical. Let's pick one of these. So what if you want to know what are some of the options I can do with TensorFlow? All the information can be found here under Keras. So you have to know where you're looking for. So here, what I want to know is what other evaluation metrics I can specify. So you will go to metrics. It should be, so there should be a link here. In the attributes, it talks about, you can bring up these different metrics. And oh, okay. When you do compilation, when you compile the model, there's an option to provide additional metrics. So metrics here. So when you specify model compilation, you have to provide what kind of metrics you want to calculate and keep track of. We did accuracy as one of the standard evaluation metric for binary classification problem. Additional metrics can be found here. So these are all the metrics that you can do. Some of these will have a string name, similar to accuracy, you can simply provide. Some others don't have an easy string name for it, such as false positive. Let's say false negative. For these more complex metrics, what you want to do is you create an object using TensorFlow, and then provide the metrics as one of the options. So provide the metrics as a list. So after accuracy, you can add more. We imported Keras. That metrics. False negative, make sure you define the object, and then there you go. So I will run this, and then this time it's training for 500 epochs. It's going to take more time, so we'll wait a little bit. In the meantime, one of the benefits of packages like TensorFlow is that sometimes you don't know how long to train, right? Before it's trained sufficiently. So with Python solutions that we had before, we have to guess. Let's say we train for 50 epochs. We look at the results, we look at the cost curve. It's not enough. What do? We go to the very beginning, change the update the number of epochs, and then run it over. Next time I may train for 80 epochs. What if it's not enough again? I have to do it again and do 100, and then again 150 until it's all done. But the benefits of these mature packages is that you can continue to train without losing the progress. So that's the benefits of it. Once you have defined the model object here, let's say you train for, I train for 500 epochs. You look at the results, it's not good. It has more potential for improvement. Let's say it's underfitting, right? If it's underfitting, you should train more. So in that case, you can run the same code, model object.fit, and then provide the additional epochs that you want to train, and then it will keep training. It will train from the point that you stopped, and then you can continuously do that until you're satisfied. So that's the ability to not waste your time of the training steps is another benefit. All right, 500 epochs is done. If you look at the logs, one thing you notice is that you have additional metrics here, the number of false negatives. So we have 6,000 data points. It's making 1,000 or so false negatives, so it's not good. Accuracy is only, it's 77%. Can be improved. If you go all the way down to the end of 500, you see that accuracy is over 90%. That's pretty good. And then false negatives is reduced to 600, 10% of the total data set. That doesn't mean that the false negative rate. False negative rate is calculated specifically. So we'll talk about next week. Anyway, by this point, the model, the training process is deeper. The training is more complete. The model appears to be doing better with more training, and we also have different or more metrics being tracked. So if you run it again, this time we're tracking 3 things instead of 2. And if you look at the weights now, it's certainly going to be bigger. You see the largest coefficients in the range of 4.5 or so, or negative 4.5. As the model keeps training, some of the weights will pick up signals to emphasize those dimensions. That's how it works. So after 500, you get something similar to 90%. And some of these performances and weights always go, loss always go down, almost always. Accuracy doesn't always, just because of small randomness, but overall it goes in that direction. So with 500 epochs, I'm not going to retrain this. With 500 epochs, let's take a look at the cost curve. So, initially training very fast, slows down, linear trend, and then slows down further as you train more. So these regions are where the model has some trouble learning, even if it's reducing the cost or reducing the loss function, is still not translating those learning into accuracy. But after 100 or so epochs, the accuracy start to learn fast. From this point on, if you keep training, then you can expect that the curve is going to flatten even more. The increase in learning is not going to be dramatic, but it's going to continue to learn a little bit more. The ultimate, the best possible accuracy is in the region of 93%. So the best that the model can do without overfitting is 93%. After that, the model can overfit, and then, training set accuracy continues to increase, but the test set will drop. Now, so after you have fairly good achievement on a result on the training set, it's time to look at overfitting and see if the model is overfitting on the test set. So, using some test codes. Here I specify for both 0 because there's really no need to look at the log. On the training set, it's not working. Let's see. Oh, okay. The reason it's not working is because now we are tracking 3 metrics, and the original codes only unpack them into 2. So you either want to, if you want to retain the false negatives, then you have to give it a name here and say false negatives, or you can ignore the third parameter, use an underscore. So on the training set, the accuracy is 90%, 90.3%, as we know. What's critical is on the test set, what's the accuracy going to be? Very close. So what this means is there is no overfitting, and then there might be underfitting because there might be potential to achieve higher accuracy on both the training set and test set, but with 90%, it's already pretty good, So you can experiment more by training more. For instance, we can do this. We use this to train 100 epochs more very quickly. So on the training set, it keeps the progress, right? It was already at 90%. It keeps training from that point on. And then after 100 epochs, accuracy increased to 91%. The only downside is that you are not going to be able to put the 2 histories together. So the new histories, are kind of lost. But the model is improved, and we'll look at, let's see, how do I get, okay, with the new model, we evaluate on the training set again, we should get 91%. And then on a test set, let's see what we get. We're looking at 91%, even higher than the training set accuracy. So that means the additional training was able to improve the model fitting even more. And there's, at this point, there's still not any overfitting going on. So the model is healthy. You can train even further, right? As I said, you don't know that beforehand, but after the fact, I know that the model has potential to be trained to 93%. But if you keep training more, you probably expect the accuracy on the test set drop below that of the training set. So training set might be 93%, test set also 93%, but when training set get to 98%, test set maybe, may remain to be 93% or maybe even below that because of overfitting. So that's a base version of comparison. After hundreds of epochs, you can expect 2 approaches to get to the same result, So, but the efficiency of TensorFlow is much higher because there's less coding, there's less opportunities for errors. You don't have to debug that much. And then it also trains faster. Computation is faster. So I will let you explore the rest of the improvements for using TensorFlow by yourself. And then certainly when we come to the point where we start the project, we will revisit some of these techniques, right? At this point, it's not, continue to learn, but we'll save the demonstration for later. All right, any questions? No? That's all I planned for today. So what do you want to do? Go home? Okay. Yeah, I mean, all the videos are online, right? You should have the freedom to plan your own study. That's the benefits of having the videos. So stay if you have questions. Yeah, stay if you want me to demonstrate other things. Otherwise, let's call it a night.
Thank you, Professor.
Sure. Are you still in?
Sorry, Professor.
Are you still in Houston?
Yeah.
Okay. I hope you'll be able to join next time.
Yeah, of course, sure. Thank you, Professor.
Thank you.